It's a great pleasure to welcome David Kazhdan from Hebrew University, and he will talk about joint work with Giovanni Felder and Alexander Polishchuk. David,
okay,
the board is yours.
So I present results, which you see here, and some work in progress, which are a continuation of Witten's work on super theory of measures of low genus. In my talk, I assume familiarity with the language of supermanifolds. Introduction. The partition function in the perturbative string theory is presented as a formal series where the coefficients Ig are integrals of a submeasure μg over supermoduli stack of supercurves genus G. And the measure comes from holomorphic Mumford form and the canonical Hermitian form of Hodgkin. In the case of genus 1, there is no problem. The integral is well defined, and it's easy to see that it vanishes. In the genus 2, there exists an algebraic projection from the modulus space of supercurve to modulus space of usual curves, such that push forward to a measure μ2 is 0. So one can declare that I2 is 0. But the absence of the projection necessitates a different approach to a definition of the integral. So this, in our work, we really concentrate on the definition of the integral Ig for G equal 2. Some results which you use are true for any genus, but the last step is only for genus 2. The supermeasure on the modulus space Sg is known to be continuous only for genus less than 12, but even in this range, there are two problems with a rigorous definition of the integral. The first problem is the absence of the notion of integration of non-compact supermanifolds. To define the integral, one has to find a smooth quantification, x bar of x, and a divisor such that its complement is the regional supervariety. Note that for supermanifolds, such a divisor is to be defined. It's not, it's additional data. A smooth quantification of a modulus space of supercurve genus G was defined by Bellini, but the definition of a divisor on infinity was missing. The second problem comes from existence of the poles of the measure of this divisor. By choosing a cutoff function, one can try to define and regularize the integral. But even when one succeeds, the result will a priori depend on the choice of cutoff functions. So these are two problems with definition integral before we start computing. In our paper, we resolve the first problem by defining explicitly a divisor delta and the quantification of moduli space supercurve on at infinity. We deal with the second problem only in the case when genus 2. In this case, we define a class of cutoff functions rho such that integral, which a priori depends on rho, is well defined and does not depend on the choice of cutoff functions. We hope that it will be possible to extend this approach to define integrals in the case of higher genus. We start with definition. A family of smooth supercurves is a smooth morphism from X to S of relative dimension 1, 1, together with distribution, it is subbundle in the relative tangent space of rank 0, 1, such that commutative brackets induce an isomorphism from. Locally, there exist relative coordinates. Such a distribution is generated by a vector field of this particular type. In this case, it's easy to see the distribution is the inverse of relative cotangent bundle, and the quotient is square of its relative cotangent bundle. So the pairing could be an isomorphism. Dually, we get a map from relative one forms to relative cotangent bundles, and therefore derivation data from functions to relative cotangent bundle. For an analytic family of supercurves, there exists canonical exact sequence. Fibers of a map carry the spin structure. If the spin structure is such that it doesn't have non-trivial sections, then the push forward of canonical bundle is locally free, and the connecting map is an embedding on a subbundle, which is related to superperiods. We use the fact later that in the genus 2, H0 is for even supercurves is always 0. Deligne defined the notion of stable supercurves. A stable supercurve is a proper flat, relatively coherent holomorphism together with derivation, where omega is relative dualizing sheaf, such that following three conditions satisfied. On the open subset, there is open subset on which it is smooth, which is smooth of dimension 1, 1. The reduced map is family of usual stable curves, and on every geometric fiber, the induced map is isomorphous. It's easy to describe stable supercurves over a point. It is just a pair of stable curve and a torsion-free sheaf L of rank 1 with an isomorphism. Near every node, I mean, on a singular point on C, either C is locally free or is locally isomorphic to ideal sheaf of the point. The former case, the node is called Ramon, and the later is called Neves-Schwarz node. Deligne, and some work afterwards, defined a compactification of modulus SIG, which is modulus stack of stable supercurve of genus bigger than or equal to, which is a proper Deligne-Mumford superstack on appropriate dimension. And the bosonic truncation is a modulus space of stable curve spin structure, as in the paper or Kahn-Alban. Analogous results holds for modulus stack of stable supercurve with punctures. There are two kinds of punctures, Neves-Schwarz and Ramon. Neves-Schwarz punctures are smooth mark point on stable supercurve, while Ramon function corresponds to relative Cartier divisor, smooth of dimension 0, 1 over a base, with a certain behavior of distribution is stipulated near this divisor. We'll need this. Let me come back. Sorry, I jumped. We'll need this Ramon modular punctures in the study on the boundary divisor. The bosonic modulus stack is the modulus stack of stable curves with generalized spin structure. Since for a stable spin curve, the parity of a dimension of a section of a spin bundle is the deformation invariant, the space is two component, given the node. The same is true for a moduli space of stable supercurve Navier-Schwarz punctures. In the case of genus 2, which in the end will be interested, the integral blows only near the even Navier-Schwarz component. Therefore, we concentrate analysis of superstring supermeasure to this neighborhood. The first step in the definition of integral is construction of the boundary divisor, delta. This construction holds for any genus. So let pi be universal stable supercurve and J the complement to nodes. Similarly to classical case, we consider the Bayesian of a push forward, which is a line bundle over a modular space G equivalent with trivialization on the open locus on smooth supercurves. The first theorem is the section extends to a regular section of this bundle on the whole, on the complete compactification of supermodular space, and the divisor of zeros of this section is a normal crossing divisor. So this is the definition of this boundary divisor. This boundary divisor is a union on effective divisor delta R, delta N, such delta R is supported on the locus of stable supercurve at least one Ramon node, and delta S with one Navier-Schwarz mode. The relative dualizing sheaf is locally free near Ramon node, but not locally free near Navier-Schwarz mode. However, the push forward of square of this bundle is a line bundle on the whole universal stable supercurve, which is noted as if it is just square of a relative canonical bundle. As in the classical case, there are natural clutching isomorphisms involving modular space with Navier-Schwarz punctures. We have the Navier-Schwarz part of a boundary divisor. We have a map of modular space for smaller genus, which correspond to two possibilities when it is when we consider union of two different curves, smaller genus, of one curve with singularity. There exists analogous morphisms for Ramon nodes involving conditional principal bundle, but since we're interested only in behavior near to Navier-Schwarz part of the divisor, I will not discuss the Ramon node part 2. Now we'll talk about Mumford isomorphism. First of all, I remind a construction of Mumford isomorphism for smooth supercurves. This construction is based on the Kazhdan-Spencer map. This map from tangent space and has two first direct image. Here, which comes, this map is a boundary map of a natural exact sequence. This Kazhdan-Spencer map defines the Kazhdan-Spencer isomorphism of a relative of the canonical bundle, on a modular space of curves with Bayesian of direct image of relative canonical bundle, square minus square. Let X be the universal supercurve Then we have a Mumford isomorphism, which identifies the fifth power of Bayesian of direct image of O with canonical bundle on a modular space of supercurve. This Mumford isomorphism is a composition of three maps of Kazhdan-Spencer isomorphism, the third duality isomorphism, and the isomorphism, the computation of Bayesian of a direct image of cube of a relative bundle, obtaining for superversion of the Lin's determinant bundle formats. The second step in our definition of integrals Ig is a construction of the extension of a Kazhdan-Spencer isomorphism to stable supercurves. This construction also holds for any genus G. We start with construction of an extension of Kazhdan-Spencer isomorphism. This construction is presented here and kind of very similar to the construction in the smooth case. It also comes essentially from the boundary isomorphism corresponding to exact sequence. The only thing that instead of tangent space, we consider logarithmic space, which are tangent to boundary divisor. This produces Kazhdan-Spencer isomorphism. Let S be the family of stable supercurves. Given a pair of even line bundles over X, there is canonical delete isomorphism between Bayesian, which is real, kind of essentially saying the Bayesian push forward is a quadratic function. On the locus, when a relative canonical bundle is locally free, this leads to a couple of isomorphisms, which are written here. The isomorphism, 1 second. The first isomorphism extends to entire modular space, while the newly local freeness of a corresponding relative cotangent bundle. On the other hand, the second isomorphism acquires a pole when you extend to the compactification. More precisely, we construct the isomorphism between Bayesian and Bayesian push forward and the minor third power of Bayesian with a pole in the Weierstrass band. This pole is what creates later the problem of integration. Combining these steps, we get the description of a canonical bundle. Now we discuss in general the integration. To define the cycle integration, we'll discuss a little later the problem. To discuss cycle integration, we consider the fiber product over so SG bosonic is modular space of curves of genus G with spin structure. We consider fiber product, which means we essentially consider together all spin structures. We define the bosonic quadridiagonal as a normalization on this fiber product. Using the local structure of the maps, one easily check that this normalization is smooth and the corresponding maps looks locally given by simple formulas. Recall that to get the string supermeasure, one uses natural Hermitian pairing defined on the open locus corresponding to the spin structure with no sections, which can be viewed as non-degenerate holomorphic pairing between push-forward analytic and analytic bundles. This is defined near the diagonal in the product of U with its complex conjugate. The later space has the same topological orbit field as U, but holomorphic functions on it are anti-holomorphic functional. Passing to determinants, we get an element determinant of this map, which is section of Berezin times Berezin bar, well defined near the diagonal, and even near the bosonic cloud diagonal. On the other hand, we recall that we have Mumford isomorphism, which we described before, and therefore we can define a supermeasure, which is a section of canonical bundle on U times the opposite. There is a theorem that this for genus less than 11, the supermeasure sets regularly to neighborhood of bosonic quasi-diagonal. But next, the problem is the supermeasure has poles near boundary divisor. And to define the integral, we'll analyze the behavior near the boundary of a compactification. But before we do this, we discuss a general problem of integration over submanifolds or supermanifolds. The super analog of integration of a holomorphic section of a canonical bundle or complex manifold of a cycle of a holomorphic section of Berezin is the integration of a holomorphic section of Berezin over CS manifold. So usually, if you have n-dimensional complex variety and you have top holomorphic form, you can integrate it over any real subvariety of middle dimension, of real dimension. It's not true in the super case. To define the integration on the submanifold, you have to define CS structure on the submanifold. A definition. A CS structure manifold of dimension, Mn, is locally space, locally isomorphic to ball in Rn with structure shift called smooth functions times exterior power. For if M is equal to 0, it means you have usual manifold, not a super manifold. Then it is the same as structure of smooth C-infinity submanifold. However, there is no canonical structure of C-manifold on general real submanifold or bosonic reduction of complex supermanifold. Fortunately, we'll find such substructure for the quasi-diagonal. So let X be the supermoduli space. So far, we defined the bosonic quasi-diagonal as topological orbifolds equipped with inversion in the product. We can consider the sheaf which we just obtained from holomorphic function on the product. The structure sheaf of C structure we're going to define contain this sheaf as a subsheaf. In order to construct the CS structure, sheaf of CS structure, we use additional geometric data. Namely, we consider the ideals of boundary divisors. From these, we get ideals which denote A minus data. Using the local form of the data, we construct a natural C infinity completion and provide the structure of C manifold to quasi-diagonal. It is not a difficult but not completely trivial construction. We now can integrate compactly supported smooth section of Bayesian. We can integrate all this compactly supported smooth section of Bayesian CS manifold. Similarly, one can integrate section of holomorphic Bayesian over C orbifold. Our plan is equipped the normalized we equip the quasi-diagonal with structure of C manifold. So there is smooth morphism, and we can try to integrate the pullback of our supermeasure mu over quasi-diagonal. But since mu has poles along boundary divisors, the integral, to define the integral, we require to produce regularization. We provide regularization by using cutoff function to regularize the integral. But even when such regularization is possible, a priori, the regularized integral depends on the choice of rho. From now on, I restrict myself to the case of genus 2. Until now, we consider case of arbitrary genus, but from now on, we specialize to case of genus 2. So as we have seen, the Mumford 4 has a pole of second order near the Schwarz part of a boundary divisor, and first order pole near Ramon part of a boundary divisor. Using the property of period matrix, one sees the integral near Ramon divisor converges. But because of second order pole near the Schwarz part divisor, we'll have to provide regularization. Yeah, okay. This I just repeat myself. So we start with detailed description of behavior of supermeasure near Navier-Schwarz part of the divisor. We consider one can see the Navier-Schwarz part of the divisor has components which correspond to separating and not separating nodes, and the corresponding components correspond to even and odd spin structure. The only second order pole appears in this separating node corresponding to even boundary structure, which is given as clutching morphism with S11, which are even component of modulus space of supercurve of genus 1 with one Navier-Schwarz function. So this way we had to consider modulus space of curve structure, puncture, because only in this case we can describe the behavior of boundary device. To simplify the presentation, I only consider the smooth part of the locus B, which correspond to pairs of elliptic curve, each with a non-trivial point of order 2, which define and spin structure. So let Xi denote the corresponding supercurve of genus 1 was one Navier-Schwarz function with local superconformal coordinates near the puncture. And we consider family of supercurves, one Navier-Stokes over odd one-dimensional affine line varying the Navier-Stokes on X side. Joining these two supercurves along Navier-Stokes and letting parameters modulus of curve area, we get a family of stable supercurves of genus 2 lying entirely in the boundary of divisor of separating Navier-Stokes. So as usual, you can describe modulus space of curve of genus G near divisor by kind of gluing together modulus space of curves of smaller G. There exists a natural extension of above family to family of stable supercurves depending on extra formal parameter and using the standard deformation of the Navier-Stokes node given by explicit coordinates. This construction also makes sense in the limit when elliptic curves in the boundary become Tate curves, acquire singularities, but I will not discuss it. In this case, we can give very explicit description of the behavior of our measure in terms of these coordinates. So we have some kind of standard measures, or standard section of the Bayesian on the side, which holomorphic, anti-holomorphic part, and that's multiplied by some function. This function consists of kind of 4 terms: mu0, mu1, mu1 bar, and mu1, 1, where mu I have, so the second order pole in both T and TR, and mu1, 1 has first order and T bar. When we start integrating over supermanifold, the terms correspond mu0, mu1, and mu1 bar will disappear. So really our only serious problem will be with mu1, 1 having pole as 1 over divided by T bar. Moreover, if the restriction, you can multiply mu1, 1 by T bar, then it will not have a pole. And when restriction on a bounded divisor, which is a product of holomorphic and anti-holomorphic part, it be identified with product of analogous string supermeasures on 2 copies of modulus space of curve genus 1 with 1 Navier-Stokes. This factorization is a kind of basic feature which we expect to hold for higher genus, which should provide possibility of regularization. But now we define a class of cutoff functions. We define a class of admissible regularization, which will show that the corresponding regularized integral does not depend on choice of regularization. The class C consists of C infinity function of the open neighborhood of a diagonal which satisfies the natural condition. It's not negative, that it's very, has zeros essentially, second order on the, it is defined in the neighborhood. It belongs to ideal generated by this ideal we discussed when we discussed CS structure, and satisfy factorization condition at the boundary. The factorization condition has to do with natural map, mapping the boundary delta 1, 1 product of 2q delta 1, 1, where it's the analog quasi-diagonal for genus 1 moduli space. That cutoff function is used in Hermitian form on the power of the normal bundle to the boundary. The normal bundle factorizes canonically the product of line bundles on delta 1, 1 with marking point. And we require, this is a conditional cofunction, that Hermitian form factorizes as a product of Hermitian forms. After we choose cutoff functions, we want to define this integral when introduced the parameter s. It's easy to see therefore s with sufficiently big real part, this integral is convergent. Is not compactly supported. There is no problem since it decreases fast in infinity. No problem to define integral is. From a polar behavior of a Mumford following boundary, as I see, we see that it converges for sufficiently S with sufficiently large real part. The first step is to prove that it has analytic continuation to the half plane where real part is positive. Here we use the structure of a quasi-diagonal divisor to show the cancellation of a second order pole. This is a standard kind of argument in string theory that summation of different spin structure lead to cancellation of second order pole. This is some kind of precise formulation of this phenomenon in our case. The second step is to show the existence of the limit of it. This one only needs to check near to separating part of a node component, the other component is absolute convergent integral. And there we use the precise expansion of the supermeasure in terms of gluing coordinate, which I discussed before. This usage of gluing coordinates is the main reason why we restrict, our arguments are restricted to the case of genus 0. Okay, the analysis of supermeasure near non-separating mode requires to know the behavior superperiod matrix near the boundary. More precisely, we use the fact that, like in a classical case, it grows logarithmically. So the kind of inverse of it is absolutely integral. In a separating case, the Dacko function is t equals 0, and by assumption, and it is an assumption invariant and a Stochastic symmetry, the gluing coordinates. It follows that the coefficient of the first order pole of a superstring contributes not trivially to regularized integral. This is true for S with large real part and therefore true for analytic continuation. A priori, the integral S has the first order pole for S equals 0. The residue of this pole is the integral of the boundary component, and it factorizes the product of two copies of convergent integral. Since we know that this convergent integral is 0 at the start, in the beginning for genus 1, the integral is well defined and easily computable, we see that residue is 0, and therefore integral I of 0 is well defined. The last step is to prove that the limit doesn't depend on the choice of cutoff functions. For this, we compute the change of the integral under infinitesimal variation of cutoff functions. And again, use the expansion of supermeasure in terms of gluing coordinates. The variation of 0 can be written as integral of the boundary. By factorization property of cutoff function, the restriction to boundary is sum of two terms, which are pullbacks from product delta 1, 1, where in each term, one of the factors is an integral of a measure mu1 over delta 1, 1. Since, as we used already once, this integral is equal to 0, the variation of I0 under change of a cutoff function vanishes. And so we proved that our definition of I of 0 does not depend on a choice of admissible cutoff function. Okay, this we proved, we defined the integral I0, but we didn't compute it. As I said, the existence of projection, such a push forward zero, suggests the integral should be 0, and we hope to carry out the computation, but this was not done yet. Okay, I'll stop here. I'll be glad to answer questions. Hello? Hello.
Thank you for your talk. Are there any questions? Oh, yeah, sorry. Yes.
Yeah, thank you for your interesting talk. Could you just give us a bit more of your vision of how supergeometry, or your vision, Witten's vision, how supergeometry is likely to impact physics going forward?
This is not a question to me. I'm not a physicist, don't have any idea. I'm dealing with kind of a problem which came from physics. Physicists define cosmological constant as a kind of this formal sum. For physicists, it's important sum Ig. Just let me go back to my screen. Physicists consider this sum, which is cosmological constant. It is important for them, for reasons I don't understand, that this sum is 0. So first of all, I want to be able to be sure that I can define terms of this sum. So I1 is easy to define. The definitions are in terms of supergeometry. So I don't have any other way, and physics don't have any other way to define it. So what we're dealing with, it attempts to produce a rigorous definition of the integral and then to compute it. The other thing, of course, beyond this integral, it is integral, one has to be defined, you can define correlation function when you have some insertions. So we're planning to consider, to extend our definition, at least for genus 2, to see whether we can extend our definition of cosmological constant for I2 to the case of correlation functions. That is kind of theme of future work. But once more, I don't know anything about physics, but superstring requires supergeometry, just more or less by definition of the notion super.
Thanks.
Thank you. Any other questions? Oops.
Hi, David. So, if I understood well, you focused essentially on the separating degeneration. Can you comment on issues arising in the non-separating
In
degeneration?
genus 2, I don't arise. Integral is absolutely convergent.
Oh, it was written there.
In genus 2, the only problem with integration is new separating even part. It's will not be true for higher genus. But for genus 2, this is the only. I expect, not only expect, I'm sure we could produce analogous parametrization or local picture near to other part of a device. But we simply don't need it in this moment.
But you said it would become important at higher genus. Did I hear correctly?
Definitely, there will be many problems in higher genus. And we're planning to think about genus 3, but we did not start thinking about it. I think we will first try to deal with correlation functions in genus 2,
right,
to be able to see whether we can define it.
Okay, thanks.
You see, because the basic problem is that that you need cutoff function in regularization. You cannot define integral as it is. Usually, if you choose the regularization, the answer depends on the choice. So it's really not well defined. Of course, you can provide some choice, but it's usually not well defined. The kind of zeta function regularization seems not to work in this case. At least we were not able to use zeta function regularization. If therefore, it also depends on cutoff function. To define that function, you have to use parameter S. You do it after choice of cutoff function, and the answer will depend on cutoff function. Kind of the main discovery, I would say, here is, at least for genus 2, existence of a class of cutoff functions. Such a regularization does not depend on the choice of cutoff function in this class. So the question is, even for genus 2, when they say independence will hold for correlation function, I see it as a kind of a first question to be dealt with.
Okay, thanks. Are there any other questions from the room? One more.
So I might have missed it, but maybe can you say again how your approach circumvents or relates to the problems of Donaghy and Witten about the non-projectability or non-splitness of supermodular space?
We don't use projection. In our approach, we never use projection.
Yeah, that's a simple answer. Yeah, thank you.
That's kind of really simple answer. That's exactly the whole idea. In our approach, we never use projection.
Excellent. Let's have a look. Are there any
This
questions?
in particular, it creates a difficult sense. For genus 2, projection exists. If you use it, it gives answer 0 very easily. But we don't know whether other, we didn't prove, pretty sure, hope, but didn't check that our approach also, the result will be 0. But it shows that the approach is completely perpendicular to the choice of projection.
All right, thank you. If there are no questions from the room or from the Zoom call, let's thank David again.
Okay, thank you. Bye.
And we will resume at 10 o'clock.